Welcome back to the 7th quarter of complex numbers. I'm really pleased to see that you are patiently going through so many lectures of complex numbers. In this quarter, we are going through Cauchy-Reimann equation. Herein, we are going to deal with complex functions. We have already understood complex functions. Now we will write a complex function, then try to differentiate that and try to relate various components of that to establish the Cauchy-Reimann equation. Then we shall understand the proof of this. And this forms a sufficient condition of differentiability for the function that we try to understand. Now, let us consider a function f, and let us suppose that it can be written as sum of two components. The first component is a real component, and the second component is also a real component, which is attached with an imaginary number I. So f of z we are writing as u of xy plus I times v of xy. So here u of xy is a function that depends upon variables x and y. And v is also a function that depends upon two variables x and y, and necessarily u and v for real function that comes from real value variables. So v is connected to imaginary through the multiplication with I. Now here the complex number z, where the function is depending upon z, this is equal to x plus iy. And as I said, u and v, they are real value functions that depends upon two real variables x and y. Now let us cite an example and then f of x is equal to z squared in the function. Like you consider y is equal to f of x, and that f of x we call x squared. This is what we have done under calculus and functions. Now here, in terms of complex number z, we have f of z is equal to z squared, and we already know that when you differentiate that function with respect to z, the derivative we write as f dash, and that is equal to 2z. In earlier lecture, we have followed this. Now we are getting into some another detail that we are going to raise a condition to Cauchy-Reimann equation. Now z square I am rewriting as x plus iy whole square. So here a plus b whole square will be expanded as a square plus b square plus yz. So this is x square plus I square y square will be minus y square. So that is here plus 2 times ix y. So here x square minus y square, this forms a real part, and twice xy forms an imaginary part, which we represent as ux. X square minus y square we represent as function u that depends upon xy, and twice xy is a function u represented by v. So here u is x square minus y square, and v is twice xy. That's it. Now to obtain clarity, I'll go one step ahead. I shall have a numeric values assigned to x and y. So here x is 2, y is 1. So z is equal to 2 plus I. Then f of z, which is 2 plus I whole square, if it is expanded, it appears as 3 plus 4i. Now you can employ this formula, or you can straightway go on multiplying and use the identity I square equal to minus 1. Now, alternatively, we can write z is equal to x plus iy, where x is equal to 2 and y is equal to 1, and we can substitute x is equal to 2. So here x square minus y square we are raising. X is equal to 2, y equal to 1. That gives you 3. And v is equal to twice xy. So here you can make it. So 2 times x is 2, y is 1. So that is 4. So f of 2 plus I, which is in fact f of z, is equal to 3 plus 4i. So a complex number is mapped onto another complex number and the function that covers it is z square. Now in the recap place I am having f of z is equal to z square, which is u plus iv, and u is equal to x square minus y square, v is equal to twice xy. Now the function f is differentiable everywhere in the complex plane. We have done this in the earlier lecture, and its derivative we write as f dash z, that is equal to twice z for all z in the set of complex numbers or in the complex plane. Now let's look at this function more carefully. Let's consider u of xy first. Now u of xy is x square minus y square. So when we have u of xy and we are having consideration that y is equal to 3 and x is not defined, then u of x3 will be x square minus 9. And now I intend to differentiate this function in u of xy, which is in fact x square minus 9 with respect to x. I want to differentiate it with respect to x. So derivative of x square will be 2x and derivative of 9 will be 0. So my answer is 2x. So here I am using notation del del x of u or del u by del x, where u is function of x and y. I can make a shorthand notation for the quantity as u suffix x. So this u suffix x represents differentiation of u with respect to x, and this is to merely remind me that it depends on variables x and y and that derivative is x. So this is in fact, if you gather from calculus, this is the definition of partial derivative of u with respect to x, nothing else. Now similarly we shall try to handle v, which is equal to twice xy. V is function of xy, and let us assume the value of y is equal to 3. I am arbitrarily considering this. So I am trying to find v of x3. So that is 2xy. So I am replacing y by 3. So 3 times 2, it is 6x. And the derivative of this function, I am talking about v, with respect to x will be simply 6, because derivative of 6x is 6. Now I am just making notations del v by del x, where v is function of x, comma 3, that is y is substituted with a constant value, and v suffix x, it means that differentiation of v with respect to x is 6. So a more generalized notation for this, del v by del x, where v is function of x and y, I can write as v suffix x, which is again function of x and y, and the derivative is 2y. So here when I differentiate with respect to x, y is to be treated constant, and when I differentiate with respect to y, x is to be treated constant. This is what is the definition of partial derivative of v with respect to x, nothing else. Now again that I am trying to substitute x is equal to 2, so u of 2y will be x square minus y square. So x is replaced by 2, 2 square will be 4, so 4 minus 4, 4 minus y square. So del u by del y is equal to minus 2y. I am taking derivative of u with respect to y, treating x as constant, and to give you a feel that x is replaced by some constant, I have substituted 2. So u suffix y represents derivative of u with respect to y, and the value returned is minus 2y. So a more general notation I am going to use del u by del y, which is u suffix y, that is equal to minus 2y. which is in fact called as partial derivative of u with respect to y. Similarly, I am extending the same idea to v, which is function of xy, and I am replacing x by 2. So v of 2y is equal to 4y, and vy, sorry, del v by del y, which is vy, that is equal to 4, which is more general notation for which I can use del v by del y, which is v suffix y, that is equal to 2x. So when I am differentiating with respect to y, I have to treat x as a constant, and that is what is the definition of partial differentiation of v with respect to y is. So with this, we have covered all four components and we put them together. Now look here, f of z is equal to z square, which is in fact equal to u plus iv, and u is equal to x square minus y square, v is equal to twice xy, f dash of z, derivative of z square is 2z, and ux is equal to 2x, that is derivative of u with respect to x, we have said it is 2x, derivative of u with respect to y is minus 2y, derivative of v with respect to x is 2y, and derivative of v with respect to y, which is vy equal to 2x. Now we want to make some wonderful observation here. You can see ux is equal to vy. Now see here, ux, which is 2x, ux is equal to 2x, and vy is also equal to 2x. You make out this observation. Similarly, uy is equal to minus vy. So here uy is minus 2y, and vx is plus 2y. So here you can equate this with a minus sign riding between 2. So uy is equal to minus vx. Then look at f dash z, which is twice z. So f dash we can write as ux plus I times vy. See, u suffix x I am representing derivative of u with respect to x, and v suffix x I am representing derivative of v with respect to x. So this forms fx. Now f dash is also equal to minus I times uy plus I times vy. Note that this is derivative of u with respect to y, and this is derivative of v with respect to y. Is it a coincidence? This can be coincidence, but I'm telling you in advance, this is not a coincidence. To realize this, we shall go through one more example. Let us suppose that we have another function, f of z equal to 2z cubed minus 4z plus 1, a kind of a polynomial. So let us elaborate the terms. 2z cubed, I am replacing z by x plus iy. Here z is being replaced by x plus iy. You can expand this a plus b whole cube. You can look for the formula, write it, and realize what I have written here. So here I cube will be minus I, this I square will be minus I, this I is with plus sign. Here we have x plus iy multiplied by minus 4. So here this is expanded. So here we can connect real terms together and call them as u. And here you can collect imaginary terms together and write them as v. Now here we have u available and v available. we can differentiate u with respect to x. So 2x cubed will be 6x squared minus, we are differentiating with respect to x, so y is to be treated constant. So this will be simply minus 6y squared, and derivative of minus 4x will be simply minus 4. Then differentiate u with respect to y. So if we differentiate u with respect to y, so treating x to be constant, this term will be 0. So derivative of y squared will be 2y2 multiplied by minus 6 will be minus 12y into x, x is treated as constant. Similarly, we shall differentiate v with respect to x. So it will be 12xy, other terms will be 0. So the derivative is 12xy. When we differentiate v with respect to y, 6x squared is treated as constant, derivative of y will be 1, so 6x squared minus this 3 into 2 will be 6 minus 6y squared minus 4. Now look at this equation. You will be able to realize that this term 6x squared minus 6y squared minus 4, this is equal to 6x squared minus 6y squared minus 4. So ux is equal to v, and this minus 12xy and this is plus 12xy. So here we can write uy is equal to minus vx and ux is equal to v1. So it is not an accident. This is not randomly happening. This is happening with different functions. You can try on your own with a couple of functions and develop a feeling that this is not coming back to you. So here we have started with the function f of z equal to 2z cube minus 4z plus 1, and we are interested in finding a dash z, which is very obvious we can do that quickly. And we have estimated ux, uy, vx, vy. We have established the relation between them. Now let us look at the derivative of the function, that is f dash z. F dash z will be, so we are differentiating with respect to z now. So this 3 into 2, it will be 6z squared minus 4z. We have to differentiate, so derivative will be minus 4 and derivative of 1 will be 0, where z is x plus iy, and if we substitute that x plus iy in place of z, so we are left with x into 6 into x plus iy squared minus 4. So here we can expand the bracket and we can couple things together in terms of real quantity and imaginary quantity. Here I squared is replaced by minus 1, and this I is associated with 12xy. So here this is a ux component and this is a vx component, you can realize. And this is equal to minus I times uy component plus I times vy component. So here this is equal to fxz. I mean to say that differentiation of the function with respect to x, and this is differentiation of the function with respect to y, and f dash of z is equal to fx, which is equal to minus I times fy. This is a very interesting finding. So these conditions we were discussing, they are not coincidence. There is a theorem behind it. Now, let us suppose that we have a function f equal to u plus iv. This function depends upon z, and u depends upon x and y, v depends upon x and y, is differentiable at a given point z0. Then the partial derivatives ux, uy, vx, vy exists at z0 and satisfy their ux is equal to vy and uy is equal to minus vx. This is called as Cauchy-Reimann equations. Moreover, it is worthwhile saying that the derivative of the function at z0 point x at x0 y0 plus I times Vx at x0 y0 is equal to f of z0, and this is equal to minus I times uy plus I times, this is inside bracket, minus I times uy x0 y0 plus I times vy x0 y0. This can be written as minus I times fy, which is differentiation of y, differentiation of f with respect to y. To prove this theorem, let us look at the quantity f of z0 plus h minus f of z0 upon h. When this h is approaching to 0, then this quantity must exist. Then we call that function to be differentiable at z0. Now the question is that how h approaches to 0, whether it is approaching along real axis only, or you can imagine that it is approaching to 0 only along imaginary axis. We have seen this kind of diagram before. We discussed that h is approaching to 0 this way, or in this way it is approaching to 0, or it can approach around imaginary axis also to 0, and in the opposite direction also. So both the times limit must exist, and both limits must be D cell. Now here we are not bothering whether during spiral it is approaching or not. Our theorem says real axis and imaginary axis only. Equating these two limits with each other and recognizing the partial derivatives in the expression is Cauchy-Reimann condition. Let us deal with another example. We have already did this, and if you remember, f of z is equal to z bar, that is complex conjugate of z. And if we consider z is equal to x plus iy, then its complex conjugate z bar will be x minus iy. So here u is x and v is minus 1. Then derivative of u with respect to x is 1. Derivative of u with respect to y is 0. Derivative of v with respect to x is 0. And derivative of v with respect to y is minus 1. By Cauchy-Reimann condition, we anticipate that these two quantities should be equal, which are not. While these quantities u, y and vx, they should be opposite, but they are 0. So here ux is not equal to vy, while uy is equal to minus vx. For all z, the function is not differentiable anywhere. Now I am recalling what we have done. If function f is differentiable at z0, then the Cauchy-Reimann equation full at z0. Is the reverse statement also true? My question is, are the Cauchy-Reimann equations a guarantee for differentiability? The answer is almost yes. Let's go through a theorem. Let f is equal to u plus iv be defined in the domain T that belongs to the set of complex numbers. Then f is analytic in the domain T if and only if u and v have continuous first partial derivatives on T that satisfy the Cauchy-Reimann condition. So yes, in fact, it forms a sufficient condition for differentiability. Let us roll through another example that will enlighten us how it makes a sufficient condition for differentiability. Let f of x is equal to e to the power x into cos of y plus I times e to the power x into sine of y. So this quantity I am going to call as u, and this quantity I am going to call as v. Then ux, that is first derivative with respect to x of u, e to the power x will have same derivative, cos of y is treated constant. Then derivative with respect to y, derivative of cos of y will be minus sine of y e to the x remains constant. Similarly, derivative of v with respect to x will be e to the x will have same derivative, sine y remains as it is, and v suffix y, that is partial derivative of v with respect to y, derivative of sine y will be cos y. Now the Cauchy-Reimann condition is satisfied for this part as well for this part. The minus sign value is very well prevailing there, and they are continuous in C. Therefore, the function f is analytic in the complex plane